Hello, everyone. My name is Katie Emilio, and I'm an engineer in the Professional Development Department at ACI. I'd like to welcome you to today's webinar, Discover Curing, the Secret to Durable Concrete. We're glad that you could join us. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1 PDH. Your certificate will be available in ACI University under the Certificates tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and today's webinar has been approved for 1 learning unit. This webinar will discuss curing of concrete and how it can improve the quality and durability of your concrete. Our learning objectives for this webinar are as shown on the screen, and now I'd like to take a moment to introduce our speakers. Larry Tabor is a senior structural engineer and field project coordinator in Black & Veatch's federal business with more than 20 years of experience in structural design, concrete materials, and several long-term construction field assignments at challenging projects worldwide. His field assignments have spanned almost half of his career, where he has gained invaluable boots in the mud experience. He has worked in the federal, hydroelectric, water, and power industries, designing, inspecting, and rehabilitating numerous new and existing structures and buildings, including critical U.S. government facilities. We also have with us today Joshua Carroll, and he is the Technical Director for Spraylock Concrete Protection, a Chattanooga, Tennessee-based producer of colloidal silica. Before joining the company in January of 2017, he spent over 23 years working with construction materials, engineering, and testing companies. Mr. Carroll serves on several committees with ASTM and ACI and maintains several ACI and ICC certifications in construction materials and inspection. He is the current chair of ACI 308 Concrete Curing.
Okay, good morning, good afternoon, good evening, dzień dobry, bună dimineața, bună ziua, buenos dias, wherever you're at. Welcome, or if you're in Texas, by the way, howdy. Today, as we said, curing. I won't repeat the learning objectives. They're the same as what was shown earlier. Fundamentally, though, we do kind of have a path today, and it's we could just jump straight into curing, but what you need to first understand is hydration, because hydration and curing are very much interlinked. Curing improves hydration, in fact. And of course, you need definitions, and then once we get into curing, we'll expand the topic and talk about various things. And then, of course, we have a lot of resources within ACI and PCA and various other acronymed groups, and so we'll talk about that as well. And many people say, well, why curing? It's so easy to understand. And, I know what it is. Why do we even talk about that? Well, if you think about it, what's your perfect day outside? It may be sunny and 70 degrees. Maybe it's a light breeze, that kind of thing. You're out in a park somewhere. Well, that's not perfect for concrete. Okay. Concrete would love that 95-degree humidity, no wind, maybe 20 degrees Celsius, just about perfect. That's perfect for hydration and gaining strength and things like that. Well, that can make you guys uncomfortable. We don't often have that, and like it or not, we don't always have the ability to control the weather. So because of that, we need curing, because curing provides these conditions for hydration. And then by doing that, we have very, very direct impacts to the strength, to the durability, permeability, all the ilities that we have that. The biggest thing that I see, and I've been doing this enough that I've seen a lot, and it is commonly skipped, shorted, just not even thought about. Literally 2 days ago, driving by from my house, and a neighbor's getting a new driveway, and I just predicted it, and it ultimately happened, where there was zero curing put down after the concrete was placed. And it is just dry as a bone right now here where I'm at currently. And you know what? At that point, they just shortened their lifespan of that concrete. And it's cheap, dirt cheap comparatively. Okay. So what's the definition for curing? Well, ACI has a definition. I've been involved in this particular one for many years now. And you can see on the screen, I'm not going to read all of it, but it's effectively dealing with the moisture, which you can also equate to water, and temperature. The interesting other aspect of this definition is at the very bottom. Occur so that the potential properties of the mixture may develop. Understand that what we want to happen varies depending upon your project. And so it's expectations, really, it's trying to manage and you're trying to work with. So actively helping new concrete be as good as it is expected to be is maybe a simpler way to say it. Expectations change project to project, of course. And there's many things you can do. So if you are talking temperature, which sometimes people think only water or moisture for curing, but understand that in a cold environment or a hot environment where we need to do something with thermal as well, that we have methods such as insulation blankets or foam insulation is used sometimes, nighttime placements, simply changing the time of the day, wind screens, there's all sorts of stuff that can affect that. At the same time, as I said, most people do consider moisture control to be the main part of curing, and it is very mostly the common side. And adding membrane curing compounds or adding water. You can see the photo on the right there. The guy spritzing down the area that is not fogging. By the way, that is not considered fogging. Some people have confused that one before. Any rate, so you get that there. Now, at the same time, we have other things that there's been debate within the industry and all this. And internal curing, for example, is a common topic, which we'll have a slide on later. But internal curing, for example, is a type of curing. But the timing that you do it is on the front end before you mix the concrete and during the mix of the concrete. So the timing is a bit different. So it's a little bit less traditional. All right, why do we talk about hydration? Well, like I said, it is very much a part of curing and the aspect of curing. And that's because the curing is truly helping the hydration. Where do we fit within the life cycle of concrete? This is just a fairly fast slide to show you this. And that's because it's a very small period of the window. So understand, first of all, that this entire slide covers maybe 5 months in total, probably a lot less. And that is compared to the 50, 75, 100-year life cycle that we want to have before we get rid of the concrete and replace it with something else. Hopefully we're not putting in the landfill, but it does occasionally happen. Recycled, uses clean fill, things like that. So just to see that this is a small cycle, it's a small effort, but it makes a huge difference, and you'll see that later. All right, hydration. Basically, when you take all the different things that you put into a concrete mixture, being it cement, being fly ash, other pozzolans, supplementary materials, slag, whatever, the rock or aggregate, that could be sand, that could be just big aggregate, however the mix is split apart, and of course, water. So once you add this water, things start happening, chemical processes. And so once the materials are mixed, the cement reacts with the water. And for this one, just simplifying it down to cement, forgetting pozzolans for a minute. You form some hydrates, and then those things kind of go together. They start to bond. And lo and behold, you have at that point concrete. Very weak concrete, but it's concrete. Obviously, there's a lot of things that affect the reaction, the rates, and the timing of all this. If it's hot outside, the reactions are going to go faster. If it's cold outside, the reactions are going to go slower. And this factors into our curing and hot weather concreting and cold weather concreting. At the same time, the mixture design itself impacts the rate as well. How many pozzolans you have, how much cement you have in the mixture, things like that. The reason why this becomes important for our discussion is because this graph, you'll see the green line there. This is a fairly classic representation of concrete hydration. You'll see it in many different textbooks and other webinars and things like that. And so this one really deals with rate of heat evolution versus time, but you can kind of convert that heat evolution to when things are happening and how things are happening. And that's because the chemical reactions is what's creating that heat. And so there's a stage 1, 2, 3, 4, 5. And stage 1 is very, very short. And I've got a photo here on the next slide. This is really what I'm setting up. But stage 2 is where we usually put the concrete into place. We have mixed it. We've transported it. We are now coming out the back of a concrete truck chute. usually, sometimes out of a dump truck, depends upon what we're doing. But at that point, that's where it's getting into a form of some sort or on the ground or whatever. And now it's starting to set up. And that's where we start coming in really for the curing, because you have some initial curing and things like that, which we'll talk about. But realistically, most of the curing aspects is done during stage 2 and stage 3, because that's realistically as fast as we're getting it in place, and then while it's starting to set up, and then as it's set up, and then finally it hits final set, which is when it is set up and it's hard enough that you can do more things. That all generally occurs within stage 2 and stage 3. That's important because, as you can see in here, this is a microscopic views, 2 different stages. On the left side, which this is slide 22, by the way, on the left slide, you have stage 1 hydration. And you see those long, thin, rod-like structures. That's ettrinite. Ettrinite's weak, but it's very fast. It's a very quick forming, but it's weak. So as things move around, those break. The better bonds is this CSH, calcium silicohydrate. CSH is a better bond. You can think about it. It's just a bunch of little finger-like things, and they're all kind of gripping together. So think like Velcro, where they're really attaching together. CH is kind of there. It's weaker. We actually like pozzolans because they take some of the CH and replace it. But you can start to see here, though, where if we're moving concrete around and we're, let's just say, removing the water or using up the water, these bonds can suffer. And it's a very critical time for concrete. Ultimately, the strength at the end of the day is highly affected by what we do right here. This is stage 3. And again, this is going backwards for just a quick second. This is maybe 2-4 hours, starting up at 6 hours after batching. So again, that's kind of roughly when we're putting this on and getting all the curing going and getting everything really finalized, setting it up for a lifetime of durability. Okay, so that's why we are important with curing, why we care. And so what is curing? Well, there's various types. There's 3 styles, I would say. The initial curing, sometimes you need, sometimes you don't. The trouble is it's very common for people to skip this or forget about it, not think about it even. And honestly, this is where you really run into a lot of problems, particularly on flat work, because you get into problems like plastic shrinkage and cracking and things like that that are difficult to recover from if you skip or miss this step. That becomes a very common issue. So when do you start curing? I have an entire slide on that, but the short answer is as soon as possible. What it looks like can differ, and how many steps can differ, because every situation is different. You have different weather conditions. Sometimes it's dry as a bone. There's no humidity out there. Sometimes it's just about raining. Hopefully we're not placing concrete in the rain. We have whole different discussions on that. That does happen. We actually just had a presentation at the last convention on that one. So initial curing, there's some things you can do. Fogging is a very popular one. Evaporative reducers, or retarders, they're sometimes called. Kind of the official name right now has been reducers, but those are fairly common. And a little pro tip, evaporative reducers do not work into the surface. They sit there and they eventually evaporate, and they're buying you time, basically. They're letting those reactions of the hydration occur to set things up so that then you can get onto the slab or whatever you're finishing with a different method or a more appropriate final method, basically. Intermediate curing is similar to initial curing, but a little bit different, because it's basically sets up the initial curing is before you've done your final finishing and your texturing and all this other business. Whereas intermediate curing, you're kind of done with that. But let's say the method that you've chosen, such as maybe wet burlap, let's say, to put on as a final curing method, you can't quite do yet. And the reason why is you may damage or mar the surface, and it's just not set up enough. So at that point, that's intermediate curing. That's where you would do some, typically a mixture of initial curing or final curing, depending upon what it is. As I mentioned here, there's membrane compounds, there's fogging, things like that aren't going to mar the surface, but you don't necessarily need to worry about taking back off or because you don't want to finish them in. So like you would not use necessarily a membrane curing compound as initial curing because you can't work that into the surface because you're not finished your texturing. Whereas an intermediate curing you could, because you could possibly spray it on, and that may be your final curing method actually. It just depends what you're planning on doing. Final curing is kind of that longer, big picture curing methods that you want to do once you're stiff enough and once you got it placed. This is where you really go to town on making sure you're going to get your concrete set up great for its full life. Once it's stiff enough, you're not going to damage the surface. You put out a membrane, wet, burlap, sheeting, all this business. I got a whole slide on the different types. But you can see on the right side here where you kind of look into intermediate curing and final curing and the surface finishing complete, final set, all that business. And then why would I cure? Well, I've mentioned it several times now, and I'm going to mention it several more times because it bears repeating. But durability. Of course, there's a strength component. Higher strength is very, very much impacted. And so for those engineers that know concrete is gray and maybe 5,000 PSI, higher strength should be important to you. At the same time, I will let you in on a secret, and that most of the time, and I'm a structural engineer, but most of the time, strength is not actually the controlling criteria for concrete. A lot of times it's durability. Think about it. On a road, for example, we measure durability by sort of equating it to higher strength and flexure and things like that. But realistically, what we end up replacing is when we have joint problems or we have excessive cracking, things like that. So if you think about it, durability really can be more important of, why are you replacing your driveway at your house, for example? And durability is related to the tougher surface, less cracking, improved appearance, things like that. And why is this sustainable? Well, if I don't have to replace it, then it's sustainable. Understanding that concrete as a whole is sustainable. Cement has gotten a bad rap because of the carbon monoxide, all the CO emissions and things like that. And we're working on that problem as well separately and everything. But if we never have to make new concrete, which uses new cement in the first place, then it's more sustainable. Facts. Did you know that after 90 days, about three months, if you were to place concrete, the exact same concrete, I mean the exact same concrete, and this test has been done over and over, and the data we've all looked at and everything, and these are true. If you were to simply do no curing whatsoever, no moisture control in this case, forget temperature for a second, but no moisture control for any which way, and you were to simply do laboratory in the air the entire time, compared to basically keep this thing wet the entire 3 months, which normally is not done, understand that, there's a full 50% difference in strength. Normally, I would tell you that it's more going to be the difference between the laboratory and then in air after 7 days of curing. We'll get to why in a second, but you can still see a very distinct difference there. At the same time, you can see a very distinct difference on permeability. And permeability, in this case, we can kind of relate to durability. And you can start to see the higher water cement ratio you get, the more pronounced it is, but there's still a difference down at the ratios that we are constantly using, that 4.5, that 5.0, 4.4, things like that. 0.4 starts to get about the same, and that is for other reasons because of, for permeability anyways, because the matrix is a lot tighter at that point. But those are studies that were done years ago, and they've been redone, and they're still hold true. All right, what would I pick? Larry, what's a good method? Well, people have asked me that a lot, by the way. And the answer is it depends. And the reason why is I don't know what you're doing with that concrete, and you have to think ahead. You'll see me here eventually use the term work backwards. Very often, the method you pick, you have to work backwards from. And that's because you have to make sure you're not going to mess yourself up, basically. But methods include curing compound, very popular, probably the most popular. In fact, I would say the most popular. Otherwise, some sort of wet curing could be burlap, non-woven fabrics, sprinkler hoses, fogging the entire time. I've seen it. Normally, fogging is more of an initial curing. Various types of other sheeting, things like that. You can see on the left here a little bit more extensive list. I will point out curing compounds need to follow. There's 2 ASTMs. The STMs, by the way, for curing compounds sodium silicates and stuff, a pure 309 or a pure 1315, and sodium silicates are not compatible. So that's a big debate in the industry. Won't get too much into that on this talk, but just be aware that there's a debate there. You'll notice that the evaporation reducers don't have an ASTM listed. There is no ASTM for evaporation reducers. Just that's out there. It's been in the works. We've been trying to get it worked through. Just hasn't happened yet. Internal curing we'll get to in a little bit. And then, like I say, thermal blankets for temperature, something a little bit different. All right, this is what not to do. I always struggle putting slides up of bad practices because people maybe don't understand that it's a bad practice. So that's why I've got the big disclaimers there. These are pictures from my own jobs. So I'm here to tell you, most of this was caused probably because of dirty nozzles and the workers just simply didn't understand. But I will tell you this right here, you might as well not even put it down. It's getting you nothing. It's not forming a continuous film. A membrane film, old terms used to be monomolecular film. You can see in the upper picture, on the left picture, the upper area where it does actually form that guy was doing good. And then he got yelled at by his boss, and then he started looking a lot like what was down below. And so I said, yeah, nope, don't want that one. Okay, impact. What are the impacts of your methods? Well, first, don't make a problem because you picked the wrong method. There are a lot of methods out there, and pick the right method for what you're eventually going to do. Again, work backwards. So decorative concrete, this comes up a lot. We have a task group, ACI 308 and ACI 310, which is decorative concrete. I have a task group working on this exact issue and concern, and I'll get to that in a second. Also understand that if you're wet curing, you got to be a little careful because you get a gradient, moisture gradient between the top of the slab once you turn the water off and the bottom of the slab where it's not evaporating as much. And so you can have curling, and curling can cause a crack if it gets enough and high up enough, either the self weight or somebody drives over with the forklift, whatever, it can cause cracks. So again, you got to be a little careful with that. Burlap. Make sure that if you're going to put the burlap down, you have a plan on how to keep it wet, including on weekends, in the evenings, at night. Also, how to keep it laid down to where it's not blowing away. That's a very common issue. Same with the plastic sheeting. It blows away. Plastic sheeting, though, if you're having exposed finish, you can get modeling, things like that. I'm going to put a little shout out for moisture-sensitive flooring, simply because moisture-sensitive flooring, there's a lot of litigation and things like that. You have to be careful on which you're picking. Certain flooring manufacturers can tell you how much money they've spent on removing curing compounds because you have the bead blast or some version of removal. There are evaporating curing compounds out there. Some of them take time to work, some of them don't. And so things that you want to pick the right, not just like a method, so curing compound the method, you want to pick the right style of curing compounds for in that case there. Other times you might want to water it down. You might want to use plastic sheeting for that particular one, simply because you can then pull it away. Understand that concrete has to be a certain moisture percentage. It has to be dry enough before you put down a lot of the moisture sensitive floorings. That could take time, or you have to spend money to dry out the floor. So again, think about this. All right, this is the big boxing match of the century, okay? Battle of rates. A bleeding versus evaporation. Bleeding in general, as a big picture term, is water coming out of the surface and basically leaving the concrete. There's also some settlement and some other things without getting too deep into that, but just think about water coming out of the surface. At the same time, we all know that water evaporates in air, right? If that is evaporating faster than it's coming out, the surface gets dry. And when it gets dry, that is not good. And the reason why is at that point, if you think about it on a small scale, you have the surface drying up and a little shrinkage happening, right? That shrinkage causes cracks, called plastic shrinkage cracks, or surface tears is what they can look like. They're not horribly detrimental to the structural capacity, but they can cause you durability problems, and they look really bad. And so an owner, in their mind, immediately failed. This concrete has failed, all because somebody didn't sit there and go through a nomograph or go through some other measures to start doing initial curing because they forgot about it, didn't think about it, whatever. There is a nomograph available. I will put a very strong caution on here. That's why I have it in red with a capital underlined exclamation points. You need to make sure that if you're going to use the nomograph, that you're using it correctly. There's very specific ways to measure the measurements for the temperature and the wind and things like that for this nomograph. If you just call up on your phone the local weather station and said, it's 85 degrees, 15, that is risky because it probably is not going to match it because that weather station is probably up on a tower in the air. Whereas, for instance, on this one, you're supposed to be measuring 20 inches off the surface. And it's developed, and it has the history of where it comes from. And it's evaporation over on a pond in Oklahoma, and it has 1950s type history to this. I won't get into that too much. But fundamentally, this can help you figure out how much evaporation you have. And then what you do at that point is you compare it to what you think your bleed rate is going to be. And understand I said what you think, because a bleed rate is very variable based upon the mixture. So if you have silica fume, for example, in your mix, that bleed rate is going to drop. I mean drop. It might not be bleeding hardly anything. Whereas if you have a just pure straight cement mixture with lots of water, fairly gap graded, things like that, it's going to be higher. And so you kind of got to understand what your target is. Some people would have said the 0.2 there on the screen at the bottom where the green's at and that arrow comes to the end, a rate of evaporation. They would say 0.2 pounds per foot squared per hour is a common number. I'm here to tell you with modern mixes, with some of the chemicals we put in it, that often is a little high. So, if you're going to miss low. But basically, if you run through the nomograph here and you find that you have the risk of having your evaporation rate be greater than the bleed rate, you better be doing something, or you're going to possibly run into plastic shrinkage cracks, failures, litigation, and other problems, up to including ripping it out. And so you tend to have this problem when it's hot, when it's low humidity, things like that. But understand, you can also have it on a cold winter day. It could be a cold day. It's because cold winter days tend to have low humidity with higher winds. And so if you think about it, winds and humidity and all that business, concrete temperature and the air temperature may not overcome the effects. And so you may still have that. So it's not just a hot weather problem. It can be a cold weather problem too. And this nomograph is available in 308, 305, PCA Design and Control. It's available a lot of places, and it's very similar. It's all based upon the same research there. So how long should you cure? Unfortunately, the answer is it depends. I will tell you that most of the time, 7 days is very common. The other commonly specified number in a spec is 70% of the minimum strength. Well, what happens on that, though, when you don't care much about strength and you care more about some other condition? Okay, that's where maybe that is not an appropriate duration. Whereas 7 days is just kind of a bland 7 days. If you get into DOT pavement work, for example, it's going to be 14 days. And there's reasons why 7 days and 14 days, and it has to do with what's known as the curing affected zone. If you think about a loaf of bread, that outer crust of that loaf of bread versus the inner gooey flexible part, that's what concrete gets. Okay, it gets a crust on the surface. And that curing affected zone is where it starts to close up after about 7 days. And at that point, no matter what water you're trying to shove in from the outside or trying to hold in from the outside, you're going to not do very well because you just have closed up your seal. It's a like putting a piece of rubber over top of it, right? So at that point, there's other things we can look at and do, but it starts to lose its benefit and its value. Also, by the way, understand that when you're in cold weather, curing durations, you must take into account of moisture versus thermal. So for example, you would usually stop your moisture about a day ahead of stopping your thermal. And the point is you want it to dry so you're then not freezing your fresh little baby concrete. You're not freezing that and causing other issues from freezing your concrete. You want it to dry out a little bit before you shut off the thermal. So they do vary. All right, decorative concrete. Like I said, 310 and 308 have a task group, and we're trying to get more research done on this problem. It comes down to, in decorative concreting, aesthetics is very important. It's way more important than any strength or anything like that. And I understand there's a relationship between durability and strength and looks and strength and things like that, but they really, really need the look. And so that's what's important to them, and that's the expectation, as I said before with the definition of curing. That's the expectation that they have. And so depending upon what look you're going for, what method you're using, exposed aggregate versus stamped versus, you name it, polished, whatever, there is a difference, okay? And so for them, that 1/8 inch, 1/4 inch worth of surface, and that's about as deep as the curing affected zone goes, maybe a 1/2 inch, is very important compared to other strengths or properties, okay? So it's something to think about, that if you're getting into decorative concreting, the tried and true method, maybe applying membrane curing compound, may not work for what you're wanting to do. All right, the other aspect that you commonly hear, and this is why I have slides on these, is sealing versus curing. They're fundamentally two different things. In curing, the goal is to keep water or moisture in the concrete, either by keeping what's there in or adding water. That's typically the goal. However, sealing, you're actually trying to keep things out of the concrete. So yeah, it's messing with the same surface, but the goal is different. Things like deicers or acids, things like that that you don't want to get into the concrete because they're harmful, the seal keeps that out of it. So when you see a cure and seal, because those exist in the market, understand that, you know, if you're trying to hit both of them, are they really truly hitting the best of both worlds, or are they kind of averaging out in the middle? Think about that. At the same time, if you are going to put a sealer down on a slab, for example, and you plan on using a membrane curing compound, for example, you may need to be either picking one that is dissipating, or you may be removing it because at very expensive cost, because some sealers won't work with the compounds. You got to make sure everything works. As I said before, think backwards. Internal curing. There are tons of webinars, tons of documents, articles, things like that on internal curing. So we don't have the time today, and this is slide 34, by the way. We don't have time today to truly get into all of that, but this is a high level. So first of all, internal curing, it clearly is a supplement to external curing. Some people say external curing versus internal curing. They're antonyms. I would call it more of a traditional curing, or what we have been talking about. And this is used in conjunction with that traditional curing. And there are very good reasons to use internal curing, particularly when you get to a high performance concrete or a high strength concrete, because the water cement ratios start to get very low. And when you get that low, if you're using up the water, recall back to those pictures in the microscopic level where I was showing you all those bonds. Well, if you're drying out and those pieces are pulling away from each other because they're shrinking individually amongst themselves, so they pull away, you have what's called self-desiccation. Self-desiccation basically is ripping itself apart from the inside. And so self-desiccation can weaken your concrete over time because you're literally pulling away the individual bonds that just formed. So to stop that, that's what an internal curing can help you with. Basically, if you look on the bottom right there, external water is added for external curing, internal water is added for internal curing. Makes kind of good sense. How it's added, that's a whole different topic, but generally you use lightweight aggregates, superabsorbent polymers, things like that. You wet them down and you have these little buckets of water inside your mix. And when there's a negative desire for the water, it gets sucked out of those little buckets and is used up within the concrete for hydration, things like that. So if it's available in there, because remember, the curing affected zone for the external water, you can't necessarily shove more water in after a particular time. And so this water then is available for use for hydration to improve the strengths, improve the reactions, and keep the good things going, keep the hydration going. Because most of the time, by the way, high performance concrete uses supplementary cementitious materials like slag cement or pozzolan like fly ash, things like that. And those reactions, A, can be slower, and B, they can be secondary. And so because of that, you want this extra bit of water available when it's needed. There's a report right now, and Josh will be talking about it in a minute here, the other half of this, which is we're developing a guide for this, but there's a report there that works it. Okay, so what's hot? Wouldn't worry about it. Whoops, they don't actually define what's hot, and that's actually explicit and that's specific. They intentionally don't do that, and that's because it depends on a lot of things. And so the short answer is start advanced planning. I say 78 to 85-ish. Some people will go a little lower. Some people might go a little higher. If you don't have a plan in place and then it gets hot, you're probably already behind the power curve and you're going to get in trouble. So start thinking about it ahead of time. Mass concrete, especially, I'm going to tell you that, it's counterintuitive, but during hot temperatures, you might actually need some insulation blankets. And it's because you're trying to avoid the differential temperatures and the max concrete temperatures and things. So you have different goals. Also, if it's hot for a long period of time, things get just generally hot. It's a thermal mass problem, right? So all your aggregate piles get hot, all your water stock, depending upon what you're doing, your cement gets hotter, all this stuff gets hotter, and it makes your overall mix hotter. Well, hot stuff makes quick reactions and causes other problems. 305 is the main source of information for that. So what do you do? Well, there's a lot of different things here. I'm not going to read them all or talk too much to them because it's related to curing, but it's really more of a hot weather concreting topic. And so you want to, in general, do things that are going to cool the mix down or at least flatten that curve. You know, with COVID, we all discussed flatten the curve. And so you want to not have those peaks and spikes of hot temperatures that can cause you a lot of problems. You want to have it more of a slow burn. And these things here help delay that. Conversely, while getting a cold beer might be nice occasionally, cold concrete generally is not. Cold concrete hydration just stops basically as it gets down to certain temperatures, and everybody kind of argues about what those temperatures are. But at the same time, just to understand when it does get cold, 306, which is cold weather concreting, has come up with about 40 degrees. You have problems and you got risk and other things. Because if you freeze even once before you gain a little bit of strength, you can permanently impact your strength by 50%. You just took a 5,000 PSI concrete and made it non-structural concrete because now it's only 2,500 PSI. And that's real early on, understand that, and that's where some of this initial curing comes into play, because at 500 PSI, 500 PSI is going to occur in a few hours. So you have to think about that. Picture on the right there, it's obviously cold. They're getting ready to place concrete, or they just have, actually, I think that now they're cold. In that picture, they just had. And so you got other problems. 900 train concrete becomes more susceptible simply because it doesn't have those little capillary void systems, which are the pressure relief that if you do happen to freeze concrete, you can move the extra frozen water, because frozen water is bigger and takes up more space than water. So 900 train concrete becomes a lot more susceptible. Okay, but understand the definition of cold weather. You need to look at your spec. You need to look at the different guides, because specs, guides, and everything else all do vary just a little bit. So you want to check that out. All right, like hot weather concrete, what can you do in cold weather concrete? As I said before, make your plan before placement day. If you're waiting until placement day, you're in trouble, and there's not a lot you can do. You're just in trouble. Insulation blankets are very common in America, but then you go overseas and they're not as common. So what can you do there? Well, admixtures help with, instead of retarders, which you would use in cold weather or in hot weather. In cold weather, you can use accelerating admixtures, non-chloride, of course. But there's other things you can do. Simply changing, if you're going to use a sheeting material, for example, instead of using a clear or white sheet, use a black sheet or a dark colored sheet for the curing materials. The sun provides a lot of energy, helps warm stuff up. But the key point here is make your plan well before placement day. That's key. Consider it, don't forget about it, okay? So with that, I would like to hand it over to the man, the legend, Mr. Josh.
Let's talk about, regarding the ILADs, as Larry mentioned earlier, durability, sustainability, and responsibility of curing practices. In reality, we want concrete to last for a very, very long time. And we're talking 50 years, 100 years, or, even longer if possible. Unfortunately, we're seeing sometimes where that doesn't happen. One of the quickest things we can do, cheapest things we can do, like Larry mentioned, is curing. And you start looking at a 50-year service life, 2,500 weeks, and we're talking about that 7-day window. So in 1 week, we're looking at 0.04% of a curing versus the life of the concrete. Ken Hover got a wonderful logarithmic scale showing how a small amount of time period for curing, comparing to that, actually shows exactly what that is. But let's look at durability. PCA's got a wonderful quote that says there are many causes of concrete deterioration, and most of these involve either the movement of water, of moisture, or the movement of species such as chlorides and sulfates dissolved in the water. Generally, the greater the resistance of the concrete to the movement of water, the lower its permeability, and the greater its resistance is to deterioration. So if we can get that curing done, we're going to increase its durability, reducing that permeability, reducing that absorption. When we do that, we got a lot of really nice things that happen to concrete. Like you mentioned, cracking resistance. Proper curing was going to limit the amount of shrinkage cracks that form. There's other cracks that we know we can't do. Settlement cracking is not really going to be affected by curing or structural things. Your surface hardness, is going to be separate from abrasion. We're looking at impact resistance. So it getting beat down. Abrasion resistance is going to go up. We're looking at how can that be affected for us, because we're going to make that concrete last longer. It's not wearing, erosion of the concrete, driving practices across it from wheel traffic and other things. Scaling resistance, very much like the abrasion resistance. When we increase that durability of it, when we lower that permeability, we're looking at the proper curing on that is going to give us a more dense, durable surface. That is going to keep us resistant to attacks from acids or other corrosive means. So gray is green. So when we talk about curing, we're talking about concrete sustainability, because that has become a buzzword. Larry mentioned the cement on it, and he mentioned it. I've said it many times over in many discussions. Making concrete last longer is ultimate sustainability, not building structures over and over again. We know we currently have sidewalks in some areas that are lasting 5 years. We got buildings that are coming down much, much sooner than what they are. One of the greatest tragedies I've ever seen is, iterated that I was a test person for a very long time. Early in my career, I had a gentleman drive me around as he was teaching me things. He was talking about in his time working that we're seeing buildings go up and come back down and testing the same place, not because somebody wanted a different structure, they just weren't lasting. And that to me is criminal when we look at sustainability and what we need to be doing to leave our future better for the next generations. So when we talk about this, concrete is going to get recycled materials, local materials, so we know we're outsourcing, you're not got a lot of transportation on it. When we get into thermal mass, reflectivity is a big one because we're using less lights. When we start looking at sustainability and lowering the footprint, you use concrete instead of a darker substance, the heat island effect comes into play. There are studies that show that we can reduce the heat island effect by 7% in major cities. For me, living in the South where it's humid, 100 degrees versus 93 degrees matters a lot during the summertime, and other places are going to feel the same thing. So anything we can do to lower that helps with sustainability. So good curing is going to help increase that, and it's a cheap way, as Larry mentioned before, allowing those reactions to complete. And one other thing, when we start looking at design, every design program out there looks at curing practices being there, could make it predictable for the strength gains and the permeability, the durability factor being in there. And again, let's look at the curing methods, selecting which ones. As the picture shows, you got a river here. You might not be able to do moist curing or wet curing for the runoffs because you don't want that water going into your local streams and rivers. So, like Larry said, look at what you're trying to do, backtrack back to where you're trying to get to, choose the proper curing method. So who's responsible for it? A lot of times being a test man, you look out there, you got the finisher or the GC who's doing it, and the people think that's who's responsible for curing it. It's absolutely not the case. The owners have got the responsibility in it to put off that little extra money. It's a cheap form of insurance for a longer lasting building, which is really what they want. Designers and specifiers picking the right one. Larry mentioned, looking at the design as from a strength standpoint, but really when we start looking at the durability factor, making those buildings last longer, that is one of those key aspects that we need to be looking at. Inspectors and building code officials, Special inspections kind of have worked on that a little bit because now you have the inspectors out there watching, making sure those practices are being done right, making note of it, and helping guide that. Working with the general contractors because they're also responsible for it too to make sure it's being done properly to get that longer lasting building that we want. And of course, obviously the subcontractors, the field crew who are actually placing these curing methods in place. So everybody's got a thing in there. And as we all know, if a good job goes, very little said, but when something goes wrong, everybody knows about it and everybody talks about it. So reputations are lost when jobs go bad. So available resources for curing. We've mentioned a couple different things. We talked about 305, 306, and that's cold weather concreting, hot weather concreting. When you're looking these up, we got the ACI PRC, which is a practice, and we also have specs. So you're looking at different ones we have here. Portland Cement Association, I pulled a quote out of there. Larry's referenced it before, a great resource. The NRMCA, another great resource, got a whole lot of packages out there to help identify different things we can do in the concrete industry to help us out. And obviously the local ACI centers, resource centers, and we've also got, ACI's got documents in Spanish for those who need those as well. So where does this come from? The curing body, 308, we've got a guide to external curing of concrete. So it's got a lot of non-mandatory language in there, but it walks through different best practices for job sites. So including the guidance on curing procedures, we talk about materials and monitoring methods. For mass concrete, maturity methods, there's a lot of information that has been put in there, a lot of painstaking research. And as things move forward and new technologies come out, this curing committee will be looking at those and referencing those as well. But again, non-mandatory language, a guideline to get better practices out there. Also, Larry mentioned before, the internal curing report. We've taken that report, we're now working towards a guide as well for internal curing to supplement what we have here for external curing. Like we mentioned before, this is not in lieu of, this is to help out and give us better concrete, better curing methods as we go through. And we're also updating that right now. It should be coming out in the next couple of years. And I want to thank Larry and other members, Eric, who was part of the committee for many, many years, worked diligently on getting our specification out. It was just published a few months ago. Went through several painstaking edits, got better definitions of curing. It gets into a little bit more, better instructions, like it says, for curing cold and hot weather, and referencing back to those two other committees. Understand 308, 305, and 306 work hand in hand to make sure that the languaging there is very, very similar and everybody's speaking from the same sheet of music. So better, clearer information on the methods, and we're still always working on definitions. The title was changed, and that was internal debate. Like Larry said, traditional versus external, but that was to separate what we're doing with the internal versus external and trying to make sure that there was a delineation that it was not in lieu of, like I said, but in addition to. So being smart with the project specifications. And here's going to be a little bit of difference in what some people see. And as a test man, what I've seen in the past, a lot of times you'll see ACI 301 being referenced in the same place as 308, 305, and 306. There's different requirements with 301 and 318 as well. So for specifiers, look at what you're actually trying to accomplish, pull the right information out, because it's going to make it easier on the job. It's going to make it easier on the general contractors and on your inspectors out there to know which ones they're following. The last thing we need is on a job site, especially if you didn't plan for anything, is to get out there the day of a placement, and all of a sudden now you've got some conflicting information and no one knows where we need to go to. So look at what you're trying to do. It's going to reduce that conflict. You're going to get a delay in your placements, a delay in construction, which nobody wants. And all that's laid out on the front end of it. So keep in mind, guides are written in non-mandatory language. Specifications are mandatory and enforceable. That's why they're broke down into two different things of a guide and a spec and all the documentations. So final thoughts. Curing concrete really does help in succession of that project. It gives us longer lasting, durable concrete. Curing directly impacts your concrete's ability to gain strength and develop durable properties, as we said. But the big thing on most jobs, when we start talking about curing, people are only looking at the moisture. It is moisture, temperature, and time. And that's one thing that a lot of people don't do. Unfortunately, what we have found is that curing is actually sometimes the most overlooked part of the specifications. You know, you got personnel that's been out there placing concrete for anywhere 8 to 12 hours. They're getting tired. They want to go home. That is where you got to have all the responsibilities falling back and everybody work in conjunction to make sure it's being placed. As Larry mentioned before, you know, some conditions require curing before final finishing, initial curing, intermediate curing before we get to there. Make sure that we know the difference between our curing and sealing. As we said, one's holding water in, one's keeping things out. Improper curing contributes to sustainability. Everyone is responsible for the curing that we have to make our concrete last longer. Ultimately, that's what we're all here to do. Make those structures last longer. Best curing practices to get us to that ultimate goal of what we're trying to do. Katie, back to you.
All right, thank you, Josh. Thank you, Larry. So we do have some questions for you guys this afternoon. Our first question is, which is more dangerous to concrete, moisture loss or elevated temperatures?
That gets to be an interesting question. First, you can hear me, right, Katie?
Yes.
Okay, excellent. Like many things in life, it somewhat depends. So elevated temperatures become a problem depending upon the makeup of the aggregate as a general life statement. There's other things. Because you can get delayed externite formation, for example. The other aspect, of course, is differential temperatures, maximum temperature differentials in mass concrete is what's referred to. And that's where it's kind of a separate animal with mass concrete or in accelerated curing techniques such as steam curing, things like that. Versus moisture loss, I would say is more of a generic or not generic is the wrong word, more of an overarching problem where it can affect everything from the average sidewalk, which I would argue that rarely gets cured properly, and therefore moisture loss becomes a bigger problem compared to maybe the more specialized things. So the short answer, I guess, is that moisture loss, I would say, is overall a bigger problem just because it affects much more styles of concrete. Whereas elevated temperatures, and understand when we start talking elevated temperatures, we're talking concrete temperatures at that point in the 160 range Fahrenheit, 70 C range. Beyond that, it starts becoming a problem child. Particularly if you have a differential temperature problem, meaning mass concrete from what is in the inner core of a section of concrete to the outer face, because there you get shrinkage issues and thermal stresses. Or not shrinkage is the wrong word. Strain really is a better word. And you get issues with differential stresses, and you can cause cracking. Hopefully that answered it. You got anything there, Mr. Josh? You good? Next, Miss Katie.
Okay. So following up on that, are there any temperature limitations necessary in curing concrete in hot weather? And I know you did mention that there's a whole another guidance on that, but maybe you want to elaborate?
Sure. So yes, there are is the very short answer. Yes, there absolutely are temperature limits. When you start talking temperature limits, you need to make sure you understand the difference between air temperature and concrete temperature. So air temperature limits, as I said, you start getting into danger zones in the upper 70s, 80s, depending upon what you're doing and a lot of other factors. And that's where that nomograph comes into play. And that's the evaporation versus the bleed rates and things like that. You can also, though, get into temperature issues at cold weather, of course. Getting too cold, hydration stops, things don't happen like it should, and of course you can freeze. And you can even have evaporation issues in cold weather. Now, if you start looking at concrete temperatures, and I'm trying to guess at which direction the question was really aimed at, the temperature limits, as I just said, were the research that Michael Thomas, a longtime member of the committee who recently passed away, unfortunately, did his research at 70 degrees C. And so the if you open up the 308 guide, for example, you will find a table in there, and it starts talking about at 158 degrees F, you need to start paying attention and doing things that can contribute to delayed etcher night formation. And then there's a scale in there and some other things you can do. And then it starts talking about what temperatures not to go above, and that's generally about 180 something, 185. That becomes important from a curing perspective, as I said, because of steam curing and all that, but also from a mass concrete perspective. So 207 and 308 work hand in hand in that, and we talk a lot back and forth. I happen to be an associate member on 207 just simply for that purpose. And so yes, there are two different kind of discussions there, it seems like. So if somebody wants to clarify, can do better.
All right, our next question is, can measuring moisture content internally be a good data point for determining curing rates, say in conjunction with measuring internal temperatures using the maturity method?
Yes, it just becomes more difficult because where are you measuring? Understanding that depending upon the depth of the slab and your age of your concrete, you start to get moisture gradients, things like that. We start looking at thermometer measurements and temperature measurements. We put various temperature probes. That is more of a mass concrete item, I would say. Whereas moisture, you can start to see the losses. Some people will also use surface testing to start getting a feel for what moisture is still coming out versus not coming out. That is a simpler and easier way to do it. And we do discuss some of those methods in the guide, and then the spec, actually in the checklist, we have a recommended test as well. And that's because it's just easier to do. Internal moisture probes, you got to make sure where you're placing it, what gradients you have, and you just have to think ahead on that. So it's often done heavily in research, for example, because it helps us understand what's happening.
All right, our next question. What are your thoughts on colloidal silica for use as internal curing?
I am handing that one off to Mr. Carroll.
Oh, you would.
I would, absolutely.
So the definition of internal curing is basically a material that is adding to what's already there. So it's a lightweight aggregate or superabsorbent polymer. Right now, what is going on with colloidal silicas, or it's blocking off potentially. So it would fall into the realm of, say, a flash slurry or something along those lines. You're not actually adding water to. If anything more, you're reducing, you're breaking off the capillary action, letting the water out, maybe, but it's not really adding the water to do what internal curing supplementation is really meant for. So as of right now, it doesn't quite fall in that category. The internal committee is looking into different things, and right now that is just not where it's sitting at.
Okay, just quick break in the action here. We're at 2 o'clock, so attendees, if you do need to step away, we understand that. Speakers, you did say you could stay a couple minutes, and I do have a couple more questions. So if you're okay, we're going to go ahead and handle those next.
Absolutely.
So, thank you. So our next question is if an evaporation reducer is used, is there a general rule for when final finishing can begin so that doesn't weaken the surface?
So the manufacturers, first of all, read and follow the manufacturer's instructions in this case, because like I said, there is not an ASTM yet for this. As a general rule, it has to have evaporated because you do not want to be working that in the surface. So if it is not yet evaporated, you have to wait. This is a tricky knife edge kind of timing thing, because if you wait too long, it can set up too much and it can impact your finishing. So that can impact what rate or how much evaporation reducer you're putting on. It's pretty variable because of the texture and the surfacing and things like that you might have already there. Many of the manufacturers also have different colors, so you can see visually. So realistically, unfortunately, it is more of a manufacturer based timing issues. You really almost have to understand which particular material you're using.
Okay, our next question is, typically, how much would internal concrete temperature rise above external weather temperature for a normal 20 to 30 centimeter thick concrete member? The attendees also curious what would be the difference for an ordinary Portland cement concrete and a sulfate resistant cement concrete.
So ordinary, first, the specific numbers, there's too many variables. I honestly couldn't answer that question. I can get into what causes the differences in generalities, though. So first of all, from a regular, in America, we would call it type 1, type 2, versus a type 5 or something like that, or even anyway, without getting into type 4s. Typically, the rate of rise would be higher and faster with a type 1 or 2 compared to a 5. That's partially why we use a 5. And so that would be the sulfate resistance or lower heat of hydration version. The first half of that question, could you maybe repeat it so I can fully understand? It was basically a 20 to 30 centimeter thick member. And,
yep.
And what was the question?
How much would the internal concrete temperature rise above external weather temperature?
Okay. So again, that varies significantly on the mixture and the initial placement temperature, and then the weather. So 20 to 30 centimeters isn't that thick, so it's not going to be as dramatic as, say, a 1 meter thick concrete, for example. It's just not going to be as dramatic, but there is an impact there, particularly if you're using what we would call as a hot mix, meaning a high cementitious materials mix. So if you've got, and I'm going to switch back to English units, 700 pounds of cement or 800 pounds of cement, it's going to be a very hot mix. And so the internal temperature is controlled by exactly two things. One is the initial placement temperature, and the other is what's known as adiabatic, or just the overall rate of rise temperatures. So at some point, there's a maximum temperature that a given mixture with a given chemistry and all the other things that play into that is going to cause a temperature rise, and you add to that whatever you placed it at initially, and that's kind of your maximum internal temperature. Your external temperature, as correctly deduced, is obviously controlled by weather, but at the same time, and this is where the curing comes in, it's controlled by what measures on the surface of the concrete, by what measures you're using to protect that surface compared to the external temperatures. So some of that could be obviously thermal blankets, but also if you're using a sunshade, for example, or some other method that could basically keep that external surface a more muted temperature difference compared to what the weather's doing. So if you have a high variability on the weather, you're better off to mute that effect, because then you can control the differential temperature, which is what I think the question is really getting at, is what is the maximum differential temperatures. Well, like I said, unfortunately, there's too many variables in that question. I just can't answer the specific numbers. But at the same time, I can tell you that most specifications will default to a maximum differential temperature of 35 degrees F between the interior and the exterior. Now that is based upon some coefficients of expansion and some other things with the aggregate that generally have the most impact. So 35F is kind of a number that everybody agrees that, yep, that works. And for some aggregates, that is a true number. For other aggregates that have a lower coefficient of thermal expansion, you can go higher. There's some research and some other stuff that was done in the UK back in the 80s, and it was published without getting into specific names and things, but it was published. Okay, there's a guy named Bamforth who did a good job, and he did some publications on that, and it showed that some aggregates like limestone, you can go higher without really causing trouble. So if you're asking what can be the maximum differential, I'm going to say 35 degrees F, just because that's usually what a spec is, but understand that that's a caveated number.
Okay, our final question this afternoon: are there any concerns in cold climates for internal curing once the concrete construction is complete and it is put into service? The attendee is specifically wondering about the internal water and if that would be subject to freezing.
Okay, maybe repeat that first part of it because you broke up just a little bit. Just want to
Sure.
make sure I got the question.
Are there any concerns in cold climates for internal curing once the concrete construction is complete and it is put into service?
Okay, so it's specifically related to internal curing.
Yes.
So it's a tricky answer to give simply because it depends. Like if I'm up in northern Alaska, for example, or northern Norway, and it gets really, really cold, then I would say the outer surface of the concrete where it would be more impacted by external factors could freeze, yes. Understanding that concrete as a whole typically will always have moisture in it unless it's just truly been all used up. And at that point, that's when you would be using more of an internal curing approach where you're adding water. Now, understanding though that these chemical reactions and the fact that you got thermal mass and all, it's not cold for days, it's cold overnight or something like that, does impact all that. And that's where, so for external curing, for example, or traditional curing, as I would prefer to say, you would have the impact be realistically right as soon as you're letting it dry. Whereas this question is more geared towards, okay, let's say a month from now, we're done with any measures on the surface, and now it's only the inside. You do have to consider that, but at some point you're always going to have to kind of consider that. And it's realistically at that point your concrete is strong enough to handle the pressures that might build up because they're basically many tensile forces. And you have a capillary void system, especially considering at this point, I'm assuming we're probably talking more exterior concrete. And so because it's more of a finished condition, at that point, you're usually in air and train concrete and you have a capillary void system. So it's not a huge issue, something I wouldn't struggle too much with, but it could be in extreme climates.
Okay. Larry, Josh, thank you guys again so much for taking time this afternoon to talk about curing with our attendees. Attendees, please answer the feedback survey that you'll see as we exit the webinar. And if you are looking for continuing education credit, but were unable to join us for the duration of the webinar, please be sure to complete the online quiz at aciuniversity.com. Please visit aciuniversity.com to see upcoming topics for our future live webinars, lots on the list for October. ACI does also offer our webinars in an on-demand format. That concludes today's webinar presentation. We hope you'll choose to join us for future learning opportunities. Thank you again.